Welcome to Hartman Math. Before we get to ellipses, we'll review of parabolas. Go ahead and work through our warm-up problem. You play when you're ready. If you're trying to find vertex, directrix, and focus, we need to get this in conic section standard form. It is y that's being squared, so we want to get the y squared, y minus k squared by itself on one side. So if we factor out the leading coefficient and then add the 1 to complete the square there, we've essentially added 2 to the right side because of the distributive property. We should add 2 to the left side. Can't have the 2 there, so let's multiply both sides by a half. And now we've got standard form. Okay? We've got our k, we've got our h, and we've got our 4p. 1/2 is 4p. So that tells us that p is 1/8. Because y is being squared, we're talking about a horizontal axis. So we would be going 1/8 to the right to get to the focus, with our vertex at -2, -1. 1/8 to the right takes us here, and then 1/8 to the left gets us to the directrix. Since our axis is horizontal, the directrix is going to have to be vertical. This is lesson 10.3, ellipses. So again, looking at conic sections. And the definition of ellipse is a set of points, the sum of whose distances from two fixed points called foci is one pronunciation. Foci is also an acceptable but bizarre pronunciation. And again, here's our generic form for a conic section. If we assume that b is 0 so that we don't get a tilt, then we're going to get an ellipse when A and C are both the same sign but not equal. So that's how we know we're going to get an ellipse in there. So in terms of our conic sections, the ellipse is the one created. When we take our double napped cone and we slice it not through the base but at an angle, we get our ellipse. So the picture that represents that, we've got our focus points, plural foci. This distance plus this distance remains a constant. So if we go to the point here and add up those distances, same as adding them up here, which is why you want to do a construction project or like an art project, you can create a really accurate ellipse with a piece of string, maybe tacks or something like that to hold these points down, and then take your pencil or pen and stretch it out and draw it around. It's going to draw a very accurate ellipse. Now the mathematical picture is going to look something like this. Here's our ellipse. We've got the two farthest points away we're going to call vertices. And the two closest points to the center we're going to call covertices. Although some texts, I think including this one, will also call those vertices as well. The focus points lie on the axis that connects the two vertices, and that's called the major axis because it's the longest segment connecting any 2 points. The minor axis connects the covertices. It will be the shortest segment that connects 2 points on the ellipse that passes through the center. The distances, the distance from the center to the vertex is A. The distance from the center to the covertex is B. And the distance from the center to a focus is C. And again, here we're talking about how you can use a tack and string and pencil to draw your ellipse. So here are the standard form equations for an ellipse where we're talking about the length of the major and minor axis. Major axis is 2a. Remember, a was the distance from the center to a vertex. So to go vertex to vertex is a plus a, or 2a. Minor axis is 2b. A has to be bigger than b. They're both positive. So if we've got, as the picture showed, a horizontal major axis, so it's going to be wide and short, then it's x minus h squared over a squared plus y minus k squared over b squared equals 1. A squared will always be the bigger denominator because a has to be bigger than b, because a is the distance to the farthest point. So if a squared is under y, you know that it's going to be vertical, tall, and skinny, as an ellipse. And the a, b, and c are connected to each other, they're related to each other by the focus equation, c squared equals a squared minus b squared. And you might think that looks a lot like the Pythagorean theorem. In fact, it comes directly from the Pythagorean theorem. So if we go back for a moment, if we look at this, look at our picture here. If you take this length a and you pull it off, it fits perfectly right here where it's c squared plus b squared equals a squared as a Pythagorean theorem problem. If you then solve that for c squared, you get c squared equals a squared minus b squared. And I always remember this sign being the opposite of this sign. And that's going to make a little bit more sense in a future lesson when we talk about hyperbolas. If the center, and h and k is the center of the ellipse, if that's the origin, then it does simplify to these equations. Example number 1, find the standard form of the equation of the ellipse having foci at 1, 5 and 1, -1 and a major axis of length 8. Is it horizontal or vertical? Well, we should use some graph paper. We should plot these points and see how do they line up. We've got 1, 5, 1, -1, and those line up vertically. So that tells us that a squared is going to have to be under the y. What's the center? So again, we can go back to our graph. We can look at it and see what point is halfway between these 2 points. Or we could use the midpoint formula, and we're going to find the center is 1, 2. So we've got our h and we've got our k. Now we're after a squared and b squared, so maybe knowing a and b first, possibly. Well, what is a? The major axis is length 8, and that's from vertex to vertex. So what's center to vertex? Well, that's 2a, so a has to be 4. Well, we don't know b yet. We do know c, because c is the distance from our center to one of our foci. And again, if we plotted these on a graph, very easy. All you got to do is count it. C is going to be 3. Now remember, c squared is a squared minus b squared. So 16 minus 9 gives us 9 is equal to 16 minus b squared. B squared is 7. We don't actually need to know b because we're not graphing this. We need to know b squared, as that's in the equation. So a squared, well, a is 4, so a squared is going to be 16. B squared we just found out is 7. We've got all the information we need. There's our final answer. Another example 1. Standard form. We've got vertices this time, and we've got a point that we're passing through. So again, maybe we plot these points, 3, 2, -7, 2. How would they connect? As these are vertices, they would connect with a major axis, and that major axis is horizontal. So that tells us in our equation, a squared is going to have to go under the x. What's our center? Again, halfway between these 2 points is going to be the point -2, 2. So h is -2, k is 2. What is a? Well, if we plotted the center, the distance from the center to a vertex is going to be 5. Now, we don't know anything about the foci, so the c squared equation is not going to really help us. But here's where we're at if we plug in everything that we know. We know h and k and a squared. We also know this point 0, 5. Where does that go? It's going to go somewhere in our equation. It's a point, it's an x coordinate and a y coordinate. It's going to go for x and y, which means the one thing that we're going to have that's unknown is b squared. So we can solve for b squared. So if we replace with 0 and 5, we're going to get this. If we subtract 4 over 25 from both sides, we can then cross multiply. B squared is equal to, if we reduce it, 75 over 7. And I would write it like this: x plus 2 squared over 25 plus y minus 2 squared over 75/7 is equal to 1. If you were to look that up in the back of the pre-cal book, it might actually say something like 7 over 75. So it is equivalent. My preference is this, because if we are looking for b, this is going to tell us b. We're looking for, how do I graph this? How far are those co-vertices or the secondary vertices away? It's going to be the square root of this. So this is my preference for how we write our answer. Example number 2, let's sketch the ellipse, identify center, vertices, co-vertices, etc. We've got our equation. It is not in standard form. To be in standard form, it needs to equal 1. So we're going to divide everything by 4. So when we do that, we get x squared over 1 plus y squared over 4 equals 1. Now, if my goal was to write the equation of the ellipse in standard form, I would not write x squared over 1. I would simplify that. But if I'm just trying to get information from this, it might be helpful to have it in this form. Our center, well, there's no parentheses, so our center is the origin. The vertices, well, the vertices come from a squared, and a squared is the bigger denominator. So that's a squared, so a is 2. It came from under the y, so we're talking about up and down 2 from the center. Up 2, down 2. So our vertices are 0, negative 2. The smaller denominator is b squared. So that's b squared, which means b also 1. It's under the x, so we're talking about left and right 1 to get to our co-vertices. So we've got our points. We can now draw the ellipse nice and round, passing through those. We've got our ellipse. Example number 3. Given an equation in general form, can we find all this information, which is going to come from standard form? And we know that's going to be about completing the square. So we want to group the x's, x squareds and x's together. We want to group the y squareds and y's together. Probably a good idea to move the constant to the other side. And as part of that process, we might want to think about factoring out any leading coefficients. We don't have it here. We do have it here. So that'll be the next step. We'll factor out the 4. Now, what are we going to add here to complete the square? 16. We'll also add 16 here to balance. What are we going to add here? 9. But there's distributive property, so by adding 9, we're really adding 4 times 9, or 36. We're going to add the 36 over here as well. Write this as a square. Write this as a square. Simplify or evaluate. And it does need to equal 1, so let's divide and then simplify or reduce. Divide everything by 64. So there's our standard form. So where's our center? 4, negative 3. H, K. A, well, that's a squared, so a is 8. That's b squared, so b is 4. And c, well, c squared is a squared minus b squared. So it's easiest to take those from the equation. A squared minus b squared is 48. So c squared is 48. So take the square root of that to get c, simplify it, and you get 4 root 3. So our center, 4, negative 3. The vertices, 8 away from the center, came from here. It's under the x, so we're talking about left 8 and right 8 from the center. So negative 4, negative 3, and 12, negative 3. Foci, 4 root 3 from the center. Again, left and right because they have to be on the major axis. So if we're talking about left and right, we don't have like terms here. We're talking about adding and subtracting from the x coordinate. So 4 plus or minus 4 root 3 comma negative 3 are the two foci. Last concept we're going to look at, eccentricity, is just the measure of how round or circular the ellipse is. So it's the ratio, the eccentricity is the ratio of C divided by A. So if the foci are very close to the center, you get a very round ellipse, very much like a circle. So we'll have a very small C and a much larger A. So when we divide those, we'll get a small number. It'll be close to 0. So the closer the eccentricity is to 0, the more like a circle it is. Whereas if it gets elongated, so less like a circle, we have a large C compared to the A. So when we divide them, it's going to be a lot closer to 1. So the closer to 1 it is, the less circular it is. The closer to 0 the eccentricity is, the more circular it is. So example 4, using eccentricity. If we're given the eccentricity to be 1/3, and we've got vertices, so what does that tell us? Well, the center is halfway between 0, 6, 0, negative 6. That would be the origin. Then we've got our equation that says the eccentricity is C divided by A, which is 1/3. And we don't know C, but we do know A. A comes from right here, from the distance from the center to a vertex. A is 6. So if we cross multiply, we're going to find out that C is 2. Let's find the equation of the ellipse. So if we're talking about our vertices being up and down, and center here, so A squared is going to go into the Y. We've got our C squared equation. 4 is equal to 36 minus B squared. That's going to mean that B squared has to be 32. So x squared over the B squared plus Y squared over A squared is equal to 1. There's our equation. That's it for today. I'll see you next time.